Hello everyone, welcome to today's class. In the last class, we have discussed how to count electrons for a given organometallic complex. So, we have seen usually the complexes are having 16 electrons or 18 electrons. Now, in today's class, we will discuss how these 16 and 18 electron complex reacts preferentially with respect to each other. Specifically, let us try to discuss 16 electron complex. Of course, by now I am sure you can give an example of 16 electron complex. Before going into that, let us discuss 16 electron complex reactivity pattern, that they often react via an associative pathway. So, there are two ways of reactions, one is associative pathway, another is dissociative pathway. I will come shortly to that. So, 16 electron complex, what you will often see is they are reacting via an associative pathway. Let us try to discuss with an example. We have one of this complex, which is again a organometallic complex, nickel complex rather. This nickel aryl chloro and then triethyl phosphine complex. Now, if you quickly do the electron count, you will find that this is a 16 electron complex, right. Now, if you want to react this 16 electron complex with pyridine, rather you are trying to do a ligand exchange, you will find that the first step will be the pyridine association with the complex. Okay. So, the whole complex remains exactly same, pyridine binds with the nickel center to give a pyridine nickel complex. Now, since pyridine is a 2 electron donor, you will find that the total electron count has gone up to 18. So, it is now an 18 electron complex. Subsequently, what you will see that one of the chloride or the chloride over here will come off, and eventually you will have again a square planar complex. Starting from a square planar complex, final complex is the one where chloride comes out and pyridine takes that place to give you, sorry, this one should be aryl, to give you the nickel complex. So, what you see here is nickel, which is a square planar complex to start with. It is a 16 electron complex reacting with pyridine, or pyridine is getting associated, that is why we are calling it as an associative pathway. Pyridine is getting associated with nickel center, 16 electron complex has now transformed to 18 electron complex, from which one chloride goes out, this chloride over here, to give rise to a square planar complex, which is essentially again a 16 electron complex. So, what have we learned? That a starting 16 electron complex, in this case it is a square planar complex reacting with pyridine by an associative pathway to give an initial complex, which is an 18 electron complex. Subsequently, the chloride comes out to give you the square planar final complex, that is again 16 electron complex. So, 16 electron complex starting material gives you another 16 electron complex. In between there is a complex that is 18 electron. This associative pathway is usually true if you have a starting material or a organometallic complex which is 16 electron, then usually the ligand exchange, in this case pyridine is exchanging with chloride, this ligand exchange is happening via an associative pathway. Okay. So, the example you will remember hopefully. In case just you want to try, you can try with other 16 electron complex to see how things are going, whether it is 16 to 18 to 16 or not. Okay. Now, let us take an example with 18 electron complex, how the 18 electron complex will react. We have seen right now how 16 electron complex is reacting. Now, 18 electron complex, these usually react. So, again usually, not always the case, but most often you will find that that is the case, usually via a dissociative pathway. Sixteen electron complex reacts via associative pathway, 18 electron complex reacts usually via a dissociative pathway, right. Now, this 8, for example, over here, if you have a complex Ml6, that is an 18 electron complex, and if you try to do the dissociation of the ligand, this ligand dissociation will give you Ml5, 18 electron complex will go to a 16 electron complex. Subsequently, you will see another new ligand L prime can get associated with it to give you L prime Ml5. Once again, this is an 18 electron complex. So, what have we learned here? That 18 electron complex starting material will give rise to 16 electron complex. Now, this 16 electron complex will react with an exogenous ligand like whatever you are using, let us say L prime, to give you an 18 electron complex. Okay, I will come to this 18 electron complex very soon. Let us discuss briefly one more time about the 16 electron complex. Now, as we were discussing this 16 electron complex, the example we were trying to give is this nickel complex, right. A 16 electron complex giving 18 electron complex and coming back to 16 electron complex. Now, of course, you might will ask me how to prove such mechanism. Can we gather some information or evidences in support of such mechanism? In order to do that, what scientist has come up with is very simply they have tried to vary this aryl group, right. How can you vary the aryl group? Aryl group is nothing but a benzene ring containing fragment, right. Now, if you substitute this aryl group with different sterically demanding group, for example, if you have that aryl group as tolulyl, means ortho position will be having methyl group, the rate of that reaction compared to when aryl group is mesityl, that means 2,4,6 trimethyl complex. Okay. Since it is a associative mechanism, you will see that steric hindrance for this mesityl group is higher or huge, and thereby the reaction is very fast for the tolulyl compared to mesityl. So, an exogenous ligand, for example, in that case it was pyridine, is coming to react with your organometallic complex. Therefore, mesityl being the bulkier one will have much difficulty in reacting with pyridine. Tolulyl is comparatively less bulky. Therefore, the reaction rate will be faster for toluene and slower for acetyl. If you really do the experiment, you will find that toluene reacts 6,000 times faster compared to acetyl. Right? What is toluene? Once again, this is going to be your toluene with orthomethyl group. This is your toluene, and the acetyl will be 2,4,6 trimethyl complex. Now, if you try to do the reaction coordinates for this reaction, it will be the first step, which is the slow one, that is the pyridine coordination, and the second step will be the faster one, and that how the reaction coordinate will look like. So, this is the pyridine coordination, and this is the one which is going to be your dissociation of chloride. Okay, that is clear now. Let us go back to the 18 electron complex. We are trying to tell you that 18 electron complex will usually react via a dissociative pathway. Thereby, Ml6, which is an 18 electron complex, will be dissociating one of the ligand to give you the 16 electron complex, and this 16 electron complex then will react with the outside or exogenous ligand L prime in this case to give you L prime M L5 complex, which is again an 18 electron complex. In the last case also, in the 16 electron case also, you have seen 16 electron complex is the starting material, it gives 16 electron complex at the end. In this case also, 18 electron complex is the starting material, 18 electron complex is the final material, but in between there is a 2 electron difference of the intermediate complex. Well, before that, I think it is better if we try to give you a real life example or more familiar example for the 16 and 18 electron complex. Now, all of you are familiar with 8 electron species, right. So, if you are talking about SN1 reaction, this 8 electron species organic compound leaves the X minus. So, you are leaving X minus and you get a 6 electron complex, which is subsequently goes for nucleophilic attack to give you substituted Y and again 8 electron complex. Even in SN1 reaction, you see that exactly 8 electron complex or 8 electron species is giving you 8 electron species. Similarly, for organometallic reactions, it is 18 electron complex that will give you 18 electron final product. Okay. Now, I will give you one real example with an organometallic species. This is a molybdenum complex. Molybdenum do wonderful complexes with carbon monoxide. For example, one is shown in over here. This is an octahedral complex. Molybdenum is having 4D5 5S1, right. Can you do the electron count for this molybdenum complex, octahedral complex? Do it quick. You will find that, so molybdenum is 6, 4D5 5S1, total 6 electrons, 1, 2, 3, 4, 5, 6. 6 ligands, each of them are giving 2 electrons. So, 6 times 2, 12 electrons and 6 for the molybdenum. Once again, this is an 18 electron complex. So, I am writing that this is an 18 electron complex. Now, this 18 electron complex, if you heat it at 70 degrees C, you will get the final product, and in presence of CO, one of the phosphine ligand will come out to give you a pentacarbonyl species the starting material was tetracarbonyl. Now, you will see that it is a pentacarbonyl species. So, one of the carbon monoxide is getting in. Once again, without counting electron, you will be able to tell that this is an 18 electron complex. 18 electron complex giving you 18 electron complex. But in between, what happens is the intermediate you get in these cases is the one where one of the phosphine ligand, let us say this one of this phosphine ligand is coming out, this PR3 is coming out from a octahedral complex. You will get a pentacoordinated intermediate, and thereby you will have a 16 electron complex as shown in here. The starting material loses one of the phosphine, and now you have from 18 electron complex you have 16 electron complex. Okay. Is it clear now? Can you do the electron count for these cases? This molybdenum case that we have shown just right now is an 18 electron complex starting material undergoing a dissociation of ligand, in this case phosphine ligand, to give you pentacoordinated intermediate, which is a 16 electron complex, and thereby CO reacts with that 5 coordinated compound to finally once again to give you the 18 electron complex, and the final complex will have one of the ligand exchanged, that is one of the phosphine ligand exchanged with carbon monoxide. So, tetracarbonyl species gives you pentacarbonyl species. Along with that, we see the intermediate formation, and that is a 16 electron complex. Just to summarize again, an 18 electron complex will undergo dissociative pathway to give you 16 electron complex, and finally comes back to 18 electron complex again. On the other hand, a 16 electron complex will undergo associative pathway to give you the 18 electron complex, and after that this 18 electron complex will undergo one of the ligand dissociation to finally give you the 16 electron complex. The starting material and the final product remains exactly same in electron count, but it will go electron count change to the intermediate species. Now, for this molybdenum complex, the one we were trying to discuss, how can you get some information that this 18 electron complex is undergoing a dissociative pathway to give you the final complex? Once again, what we can try to do is, in laboratory we can try to run the experiment where your this phosphine R substituent can be changed. Now, this substituent R could be your alkyl, aryl, and whatever you want, right. This tri R3 or tri R alkyl complex. Now, what scientists have done previously is this PR3, when this PR3 is taken by different substituent, we find that, for example, if we have PMe2PH and PMePH2, again R is varying, this R is varying, and let us say triphenyl phosphine or dicyclohexyl phosphine. So, in all these cases 3 R are there, R could be, these R could be different, 2 methyl, 1 phenyl, 1 methyl, 2 phenyl, 3 phenyl, 1 phenyl, 2 cyclohexyl. In all these cases PR3 is the general formula. The cone angle cone angle is something you need to know, you do it at your as your homework. Cone angle actually defines how bulky the ligand is compared to each other, right. Now, this cone angle will vary depending on the bulk of the substituent on the R group. For these cases, for the first case it is 122, for the second case it is 136, because the substituent is getting bigger and bigger. So, 1 phenyl to 2 phenyl angle increases, so it becomes considerably bulky. PPH3 you would expect that it is even bulkier, 145. One of the phenyl or 2 of the phenyls are getting replaced by 2 of the cyclohexyl, which is again bigger compared to phenyl, and thereby you will see that the cone angle increases to 162. So, from this series, as you see, the ligand size is increasing, the cone angle is also increasing. Now, if you look at that 18 electron complex where PR3 was there, the relative rate of these complex, when you are varying different phosphine ligand, you will find that the dissociation is faster if the ligand PR3 is bulkier. So, bulky ligand gives rise to steric hindrance, and therefore, dissociation of the phosphine becomes much easier, right. The relative rate will vary in the order. This the first one is the slowest, and then you have relative rate of 1, 240. These are not absolute value, it is relative to each other, and 4800. You see the difference in the reaction rate. This is the fastest, and it is very fast. Compared to that, the first one is very, very slow. So, as the ligand size is increasing, you see the cone angle is increasing, and therefore, steric hindrance is quite high, and dissociation of the ligand becomes much more easier. That is the first step of the reaction. So, that will be the faster in case of this monophenyl dicyclohexyl complex. It is actually 4800 times faster compared to this monomethyl diphenyl complex. Okay. Now, such an observation will be consistent with dissociative mechanism. This observation is consistent with dissociative pathway, right. If it is not dissociative, you will not see such observation. Since the steric bulk is controlling the reaction rate, higher the steric bulk, faster the reaction. So, the reaction that we were discussing earlier, that is your molybdenum complex. This molybdenum complex, bigger the PR3, these 2 PR3 you have, bigger these R groups are, one of the PR3 will dissociate faster to give you 16 electron complex. That is again, it experimentally shows that when you have an 18 electron complex, the intermediate formed for this reaction is a 16 electron one, which will undergo ligand exchange with an exogenous ligand to give you 18 electron complex. That is the reaction trend, that is the trend we see for 16 electron and 18 electron complex. Is it universal? That is definitely one of the question you might will be having. Is it always true? All the time, are we going to see 16 electron complex will undergo associative mechanism, or 18 electron complex will undergo dissociative mechanism? The answer for that question is no, it is not always true, but most often, let us say 99% cases you will see such precedence, but there are few cases which you need to know, that 18 electron complex, for example, can undergo even a dissociative, not a dissociative pathway, but rather an associative pathway. What we have seen is 18 electron complex going via a dissociative pathway. It is possible in some rare cases that 18 electron complex will undergo associative pathway. Let us try to take one of the example. Well, this is once again it is not a norm, it is a special case, associative pathway for an 18 electron complex. What we have learned so far, 18 electron complex should undergo dissociative pathway, but here we will see associative pathway. What could be the example? Let us take this rhodium complex. Okay. It is a cyclopentadienyl dicarbonyl complex of rhodium. If you do the electron count, once again it is an 18 electron complex. Now, if you try to react this with a ligand, what we expect, what you would expect, that one of the CO should come off, CO should come off to give you 18 electron to 16 electron complex. But in this case it does not happen in that way. PR3 rather undergo association. So, PR3 will add to the rhodium species, that is unusual. Then you might be thinking that 18 electron complex should be undergoing 20 electron complex formation. That is not true. What option we have in this case is, it is a eta 5 complex, right. Now, this is what is known as ring slip. One of these eta 5 complex, or this eta 5 complex will undergo ring slip from eta 5 to an eta 3 mode, and you will see PR3 is coordinating with the rhodium complex. Now, you do the electron count from a eta 5, you have eta 3, overall you will see again 18 electron complex formation in this case as well. So, this process you can call it is a eta 5 eta 3 ring slipping. Right, giving rise to the 18 electron complex. 18 electron complex is not undergoing a 16 electron complex formation, rather a ring slippage is going on. Mode of coordination of one of the ligand is varying from eta 5 to eta 3. That leaves out an option for this ligand, exogenous ligand PR3, to coordinate with the rhodium in an associative fashion. All right. Of course, this is the intermediate. Final step would be where this CO comes out and the eta 5 mode of binding of CP gets back to rhodium, and you have a rhodium carbonyl and PR3 species at the expense of CO. So, CO comes out, this CO comes out, and eta 3 now goes back to eta 5. Overall again you have an 18 electron complex. So, what have you seen in these example, or in this particular example, is 18 electron complex undergoing a ring slippage. So, without any dissociation from the metal complex, we see that exogenous ligand, in this case phosphine, is getting associated with the metal complex. 18 electron complex is very uncommonly undergoing an associative mechanism to give you another 18 electron complex. finally, one of the ligand, that is in this case CO, comes out to give you the final complex, and that is the one where we see that cyclopentadiene ring eta 3 to eta 5 mode gets back to give you rhodium CO phosphine complex, finally once again 18 electron complex. So, 18 electron complex starting material gives you 18 electron complex intermediate and gives finally the 18 electron complex product, which is rather uncommon, and thereby this is an example, uncommon example, that an 18 electron complex is undergoing associative mechanism to give you the ligand exchange. Well, once you know that cyclopentadiene can do the ring slipping or flipping is possible, is there other mode of reaction? Is there other example where we can expect such ring slippage or such mode of electronic flexibility? Okay. Let us discuss briefly other groups that are electronically flexible. What we have seen, cyclopentadiene is electronically flexible. Are there other examples? Indeed, there are. For example, you can have eta 3 allyl complex, okay, and this allyl complex can undergo again similar to ring slippage. It is now eta 1 allyl. Okay. So, eta 3 to eta 1 slippage. You can have similarly carboxylate linkage, where you can have eta 3 carboxylate undergoing similar ring slippage to give you eta 1. So, this will be a eta 1 carboxylate, or other famous example includes the metal coordination with benzene by eta 6 mode. Now, the slippage can be possible to give you an eta 4 mode of coordination. So, these are some example. Of course, there are a lot of other cases. You can see electronic flexibility, eta 3 allyl giving rise to eta 1 allyl, or vice versa. You can have equilibrium between these two things. You can have eta 3 carboxylate giving rise to eta 1 carboxylate. Also, eta 6 benzene can give you eta 4 benzene. So, what so far in the last part we have understood is, although there is a general reactivity pattern for 18 electron complex going to 16 electron complex as an dissociative pathway, and then 18 electron complex finally forms, there could be some example, there could be some cases where a ring slippage is possible from starting with an 18 electron complex. We can get intermediate 18 electron complex. In these cases, as you have seen right now, an allyl or a carboxylate or a eta 6 benzene complex can give rise to such 18 electron to 18 electron intermediate. These slippage are not happening usually. These complexes are rare. Not all the complexes with these ligand will undergo the ring slippage as we discussed, but in some cases we can expect that this ring slippage is happening. Okay. Once again, it's not a common phenomenon. It happens only in rare cases. Okay. So, with this, today's session we would like to conclude that I hope you have learned the reactivity pattern of 16 electron complex and 18 electron complex, as well as there are few examples where 18 electron complex will not follow the textbook rules, and those are the ones, frankly, those are the ones quite interesting, and those are the ones which researcher found is quite attractive for carrying out lot of unusual reactions. Okay. We will see you again in the next class. Till then, bye bye.